Our next speaker is Eric Griffis, who will be talking about Algebraic Racket, which is a new language that he's designed that was recently released on the package server, which is very cool. So take it away, Eric.
Oh, thanks, Jay. So like Jay said, I'm here to talk about Algebraic Racket. And I'm going to do that by telling you a story about Algebraic Racket. Because I've come to realize that one of the best things about Racket also happens to be one of the worst things about it. It's just so flexible. I mean, it can be so many different things to different people all at the same time. And as long as everybody does their part, it just works. But how does anybody know what their part is? And so I think that's more of a quest than a question. And for me, I'm really interested in the direct experience of programming. So, getting in the zone faster, staying there longer, getting more out of each moment. So Algebraic Racket is designed for maximum flow. So the big idea behind Algebraic Racket is pretty simple. In programming languages that have static type systems, those types describe interesting structures, or at least useful ones. But what we don't talk about so often is the fact that those structures are still useful even without the type system. And in fact, I can use them to make programming more fun and to make my programs more beautiful. And the key to unlocking the flow potential of Racket is to think structurally. And so what I mean by that is to literally orient my thoughts around the shape of the code I'm writing as I'm writing it. And so let me show you what I'm talking about. So when I write some code, in the beginning it tends to be very tall, because I'm not sure how wide everything wants to be. And later I'll go back and kind of stretch everything out so that it more efficiently uses the space. But if I zoom out a little and I keep stretching until everything fits on its own line, something interesting happens. So the common structures in the code become easier to see. And that's a good thing, because that's exactly the insight I need to start making effective macros. So when I first started using Racket, I realized that there was a handful of functions I'd use all the time. And so to save myself some typing, I gave them short operator-style names. And that worked pretty well. It made my code more compact and a little more functional. But I started to notice, as I started using these more often, that these interesting structures were growing out of the places I was using them. So here's one I call the compose totem. And it's a function. You apply it to some arguments. It spits out some results. And before I show you how this one grows, I would like to say I'd like to think about syntax as just an ordinary Racket struct type with some fancy notation and a field named E. So if I have a syntax object with the list 1, 2, 3, and I apply syntax E to it, what I get back is a list with all of its elements wrapped in syntax objects. So the first thing I might want to do in a situation like this is map syntax E over the elements, get the data out. Then I'll perform some computation on them, and when I'm done, I'll collect up the results and spit them all out. So this is the expression that does what I want, but it isn't yet a function. And this expression is heavily right-nested, so if it doesn't fit on one, it's going to be hard to work with. So one thing I can do about that is I can curry the outermost expression to create an inflection point so that the final argument's expression is free to float down to the next line. So this is an expression with a curried function in its head, right? A curried head. And I can do that as many times as I like. And when I'm done, I can stack the heads on top of each other with the compose function. And since I want this one to operate on its whole argument list, I'll stick a list constructor at the bottom. So that's pretty easy to see, right? This is pretty straightforward stuff. I've only been using Racket as an ordinary functional programming language. And since I haven't introduced any macros yet to confuse things, it's easy to think about my programs because code is just code and data is just data. And at some point, I'm going to want to grapple with macros, right? Because I'm going to want to make my own language constructs because I want to do some language-oriented programming. And if you had asked me when I first learned about language-oriented programming what I thought about it, if you told me I can get more done in less time doing the thing I love most, designing programming languages, I'd say that sounds like magic. And fortunately, I'm the kind of person who likes to understand how the magic works. So I started asking myself, how can I make Racket work harder? And for me, the answer came when I decided to implement algebraic data types, or at least the structures underlying them. So in algebraic data consists of sums and products. And in algebraic Racket, a sum is like a list of product names, and a product is like a list of unnamed fields. So products, when I first declare the data, the product names are initially bound to a constructor function that takes some arguments, produces an instance of the product with those arguments as its fields. And products and their instances are, you can compare them with equal question mark, and they print as expressions that can be read and evaluated to produce structures that were equal to the originals. And within a given sum, the products can be sorted in the order they were defined. And so another way of saying all this is that algebraic data implicitly derives Haskell's EQ, ORD, read, and show classes. And algebraic data is useful on its own, but it's way more useful once I introduce pattern-based restructuring. So in algebraic Racket, the names of the abstraction-producing forms tell me something about the shape of the form itself. So here's a function form. It's like match lambda. So each of these bracketed things is a clause, and at the head of each clause is a pattern. And here I'm just matching against some products and their instances. And at the bottom, I have a catch-all, which uses a wildcard and maps whatever that doesn't fit into my structure into a failure message. So the phi form is like lambda. It only has a single clause, so I don't need the brackets. And in this one, it's hard to tell, but this is just a single pattern. And what it does is it uses a regular expression to match against a string or a port. And it has three capture groups, those parentheses. And whatever matches those are further deconstructed by some other regular expression patterns, which then bind their data to some variables. And I can use those variables to create instances of what I have up here is a HTTP request. So like I said, at some point, I'm going to want to grapple with macros, because I want to make my own language constructs. And so one of the first constructs I made with algebraic Racket is event-let. It's a let-like form, and all it does is it wraps sync around the binding expressions, just so I don't have to do it myself. And this is really easy to implement with the mu star form, which, like lambda and phi, has only a single clause. But the star tells me that the pattern matches the whole argument list, not just a single argument. And an event-let star form is just about as easy with the macro star form, which has multiple clauses like function and has a pattern that matches the entire argument list like mu star. And everything works until it doesn't, right? So let me give you an example of how things can go sideways with macros. So here's one with syntax. It comes from inside algebraic Racket itself. And without getting into too much detail of what it does, its job is to take syntax from 3 different places and kind of tie it all together and make everything work. And if this is in the same file as all those other pieces, things just kind of work. But once I started breaking things into different files, and putting things in separate modules, then the identifiers that it was binding would just disappear. They weren't there. Sometimes they were there, sometimes they weren't. And eventually I realized they weren't there if things weren't in the same file. So it took me a long time to figure out what to do about this. I think I spent a few months asking questions that went unanswered on Racket users. And eventually I found a way to ask the right question. And somebody told me about replace context. So there's a warning here, right? Like, this is basically like the easiest way to defeat hygiene, and that can lead to even bigger headaches than my identifiers don't exist. So be careful with this. And I'm not going to tell you what exactly I'm doing here, but the gist of it is that I'm kind of saying, take the syntax that I'm outputting and pretend like the caller wrote it all out themselves. And it turns out that's not the right thing to do either, because there could be other macros, modifying the caller's syntax before my macro sees it. And when I replace context willy-nilly, I'm kind of stomping on the scopes that those other macros have added. And so the variables from other macros were just disappearing. And that was even harder to debug, but because I had an idea of how to work with scopes, it took me less time. So in the end, what I really wanted to do was exactly the same thing that datum to syntax does, which is only add context to things that don't already have it, like symbols. And just to make that a little easier to use, I created this sharp % rewrite macro that just kind of like takes the first argument and copies it to the rest. Oh, last detail. I also started leaning on syntax parameters to do most of the heavy lifting on the scope munging. That's a lifesaver. If you're doing anything that breaks hygiene, I strongly recommend you take a look at syntax parameterize first. So what happened? Why did things get so difficult? Like, we had this really easy time, and then suddenly we fell off a cliff. And I think the problem here is that once you start using Racket as a metaprogramming language, especially if you're doing it procedurally, it becomes a lot harder to tell when it's okay to think of code as just code and data as just data. Because the whole point of a macro is to treat code as data, right? So at this point, if you had asked me what I thought of language-oriented programming, I tell you, this is exhausting, right? Like, I'm doing all this extra work for what? What am I getting out of it? And so I started asking myself how I can work less hard for Racket and get back to the work that I actually care about. And again, the answer came to me when I decided to implement a feature, and this feature was type classes, or rather the structures underlying them. So in Algebraic Racket, a class is a collection of names with optional default definitions. So this is all abstract. These don't actually exist when I say class. And an instance of a class is a collection of bindings. So the definitions are not optional. And I'm still not actually binding anything. It's the with instance form that does that for me. And classes and their instances are lexically scoped. So that with instance form allows me to, for say, like, the members of this class or this instance exist only within the local scope of this block. So once I have classes and I can make instances, I'm going to want to make a monad, and with monads come do notation. So in the list monad, do notation is effectively a list comprehension. And in Algebraic Racket, I've added a twist where if I return more than one value, then they all get spliced into the result. And this is something where, like, not having a type system is quite a bit less of a headache to experiment with. The values monad is similar, but it uses the lazy do form, which just delays the computation of the monadic expressions, which in this case, the interesting one is the expression to the left of that arrow, or to the right of the left arrow. And my favorite monad is the event monad, because it's just so easy to implement, and it's very useful. So simplest implementation comes if I start by implementing the functor, where fmap is just handle event with its arguments flipped. And I can extend that into a monad, where bind is just replace event. And the return function just reduces to handle event, always event, something that produces a bunch of values. And I can even extend it further to an applicative with a straightforward do block. And in this case, it's actually handling multiple return values from the events. And it actually takes less code to do this than if I was only handling a single argument at a time. So once I have the event monad, the first thing I wanted to build with was this async values event form, which takes some number of events and synchronizes them opportunistically, and then spits out the results as multiple distinct return values. And this, again, is really, so this is how I implemented it in base Racket, and it works. But it's kind of hard to understand how, because there's all this -evt noise, and then the function is, it's sheared in half by that space above the lambda. But if I re-implement this in the event monad with the do notation, it's a little easier to see what's going on here. So async values event is a recursive function, and on each iteration, it chooses a ready event and applies itself to the remaining events. And when there's no more events to synchronize, it collects the results and then spits them out. And once I have async values event, it's easier to produce constructs that rely on events. So let's say that I have some number of threads running, and they're doing some work, and occasionally they stuff some results into an unbuffered channel. And so what I do is I created this async eventlet form so that my main thread can, just request some number of values through the channel without caring about where they came from, and then compute on them in the body. And async eventlet is easy to implement with moostar once I have async values event. And in this case, the code is actually a little bit simpler than the synchronous version. And I can do the same thing. Oh, what happened to my? OK. OK, so anyways, I think that was a lot easier than the stuff I showed you before, right? This is easy. And this time it really is that easy. So what's the difference between language-oriented programming and metaprogramming? And at this point, today, if you ask me what I think about language-oriented programming, what is language-oriented programming, I'd say, well, what do you want to make of it? Oops. And that brings us back to where we started, right? So what does Racket mean to you? I think that's a question that we should all be seriously asking ourselves. And once you start looking for that answer, you should tell us what you're seeing along the way. And once you find your answer, you should think about how much work it took to get there, and consider leaving something behind that will make it a little bit easier for the next generation to survive that trip. And I didn't make Algebraic Racket just to study Racket. I actually had some stuff in mind I wanted to build. Things like libraries for real-time visualizations, diagrams and animations, and professional audio processing. And then once I have all these pieces, I'm going to combine them and use them to produce live audiovisual demos and performances as a testament to the strength of language-oriented programming. I can do all of this in my spare time, right? And it takes a while, but it's possible. And so if this is something that you think that you can get behind financially, please take a look at my new page at patreon.com/deadbox. I think there's quite a bit more going on in the explanation there than what I'm delivering to you today. And if you have time to spend, send me an email or find me on Twitter, and let's talk about how we can get together and form a community of hyper-efficient, creative programmers that rely on Racket to get more done in less time. And if you want a copy of my slides, because I know I kind of breezed through the code quickly, you can find it on my GitHub. So thank you, and the end.